started? Let's get started. So, does anyone have any questions? Maybe from last time or from the homeworks that you're looking at? Yeah?
Were there only typos in the last question?
Yes, that I caught. Well, I actually didn't catch them. Somebody else did. Yeah?
I have a question about the first question, half A. It asks
Okay.
for the rate law for CO.
Right?
Yeah, but you cannot, but it also states that you cannot use the PSSA assumption for hydrogen radicals.
Yes. Do not use the PSSA assumption for hydrogen radicals. So the rate law will include hydrogen radicals in it. Yes.
So that's okay? But
That
it's
is, yes.
It's an intermediate.
Yes, but intermediates can be in rate laws. We just usually don't want them there.
Okay.
So in this case, yes.
So for 9.4, if you add up all the elementary steps and you get a final reaction, they say that the pyrolysis in the book, like within the chapter, is completely different than the final equation you get. So are they just choosing a different mechanism?
I'd have to look back at the chapter, but it's likely that they had different sequence of steps, or they weren't considering the reverse of one step.
Okay.
And that's actually the last example I'll go over today. Is I'll also talk about pyrolysis. And it may or may not match exactly the homework problem or what's in the book, but just as an example. Yeah. Oh, my office hours have always been decided. The TA's office hours are going to be tomorrow, period 7 through 8, and the room is to be announced, but hopefully later today. We asked about a room, but they haven't told us a room number yet. Okay, so last time you guys should have seen the pseudo-steady state approximation or hypothesis. You'll see it written both ways. And today we're really just going to continue using that for a couple of different classes of reactions. So it's just further examples. It'll help you in your homework and stuff like that. Okay? So the first thing that we're going to talk about are consecutive reactions where the first step is reversible. So generally, A goes to B in a reversible reaction, B goes to C, and you see I write that irreversibly. Keep in mind, all reactions are reversible. What I'm doing here is I'm just telling you that we can neglect the rate of the reverse reaction of reaction 2. So it just simplifies the problem, but in reality, there's always 2 arrows. So this is a very common type of mechanism. This isn't necessarily a mechanism of elementary steps, but this is a common motif that you'll see in different types of reactions, including catalyzed reactions, where A to B may be the adsorption of a species onto a catalyst, and B to C may be the reaction of that species into something else. So that's very commonly seen in catalysis. Enzymes also have this general form for many enzyme catalyzed reactions. And then another type of reaction that I'll go into more detail with here in a second is a unimolecular reaction. So if I have a unimolecular reaction, simply A to B, often how that reaction actually occurs is that I react A with another A in a reversible reaction to make A star plus A. So this is a bit maybe odd looking. A star here means a vibrationally excited molecule. So what do we mean by that? How does this molecule become vibrationally excited?
Stole a little bit of energy.
It stole a little bit of energy from what? Yeah, energy is conserved, that's good. But from where did it steal it?
Collision.
From the collision, right. You take the kinetic energy of the collision, and if the kinetic energy is high enough, then some of that kinetic energy can go towards a vibrational energy, a vibrational excitation that now leaves this molecule capable of subsequent reaction to form B. So I hope I haven't confused anyone. This is still generally this, right? Here B is, if you're comparing it to back there, this is B and B is C. But generally speaking, it's still the same type of thing, right? Two things react in a reversible step followed by an irreversible step. All right, so let's look at this specifically. We want to write the rate of formation of B. So which reaction rate should I write down? For the first or the second reaction? Second, right? Pretty simple. R2 is equal to what? K2, generally we put the K's first, times the concentration of A star. Is this an elementary reaction? Yeah, I mean, you really don't have anything else to go on. So yes, this is an elementary reaction, and that's why I know the rate law so easily. It's just rate constant times the product of all reactants, and there's only one reactant. Okay, so now I want to write the rate of formation of A. A star, excuse me. So what is that? K1 times A squared. Again, it's rate constant times the reactants. Is there anything else that needs to go here, though?
Yes. Minus.
The reverse. Why?
Equilibrium.
Not equilibrium. It's simply because it's reversible. Has nothing to do with equilibrium. So now what do I write for that one? Minus, right? Because I'm consuming A star. K negative 1 times what?
Concentration of A star.
Concentration of A star times A. Anything else? Minus K2 times what? A star. Notice how we don't have B anywhere up here, right? Everybody see that? It's just because we've written that this reaction is irreversible. Okay? B's not in here at all. Now, if I apply PSSA to A star, what can I do to this equation?
Equate it to 0.
Set it equal to 0. And why do I want to do that? Because it's easier. Well, yeah. Setting things equal to 0 is easier, but why does it, how does it help me? How do I want to rearrange this equation to make it useful?
So eliminate it.
That's right. You want to solve for the intermediate. That's the general strategy that you would employ. You solve for the intermediate because now I can substitute the expression for this intermediate into the rate equation that I actually care about, which is the rate of formation of B. Sorry, shouldn't really put these concentration terms. Okay, so through rearrangement, you get A star is equal to K1 times A squared divided by K minus 1 times A plus K2. So now I can substitute that into this rate equation for B. K2 times all of that. Any questions?
How do you determine that's the elementary reaction? I forget.
In this case, they'd have to tell you.
Did I always tell you?
Yeah, generally speaking, if you see there, if you have nothing else to go on, then that's an assumption you kind of have to make. this first reaction where I write A to B, that's not elementary, right? But again, I would have to tell you that. I'd have to say, here's the overall reaction, here's the reaction mechanism, or I might ask you to tell me what the reaction mechanism is. Any other questions? Yeah?
So applying the steady state assumption, you assume that the K2 is much, much greater than K1 or K negative, right? You assume that once they start different, it's used?
Not necessarily. It could also be, you're essentially assuming that this denominator is large. But yeah, I mean, K2 is a big part of that. But yes, that's the idea. Is once you make it, you consume it. It could be, though, that this is also large. Because that just means that you're always going to have a very small amount of it. Okay, so let's ask the question, what is the reaction order, this equation, in A? First order, second order, I heard second order. A lot of silence. It doesn't depend on the relative energies. Well, it does in a way, but it does depend. That's the point. It depends. What does it depend on? It depends on which is larger of these two terms in the denominator. Okay? If this is larger, what's the reaction order in A? 1. Right. And that's essentially saying that mathematically, this number is so small that I get just about the same rate if I just forget to put it in there. And you get a first order reaction in A. Now, if this term, K2, is much larger, then what do I see? Second order. That's right. There's many, many, many chemical reactions that take this form in their true mechanism. Yeah?
How would you describe it if they're on the same order of magnitude?
I mean, you just say this is the rate equation, and you don't use, that's kind of what I was leading up to. Reaction orders are often misleading. Reaction orders, usually when you learn about a reaction in literature or through observation, somebody says it's a first order reaction. What they're really saying is it's a first order reaction at the temperature I was looking at this pressure range, right? That when they went from 1 bar of A to 10 bars of A, they saw a linear response in the rate. So it's much more of a description of how the rate changes with pressure than it is of the mechanism that underlies the rate. Because this mechanism is not a first order mechanism, right? It could be, though, depending on where you were taking measurements. So your measurements can mislead you into thinking that you have a very simple mechanism like A goes to B as an elementary step. But that's not actually an elementary step. Even if you observed first order dependence in A, it could have still been coming from this mechanism all along if you were only looking at conditions where this was true. So yeah, that's what you want to do when you have these sort of things, is you want to look at the limiting conditions is the easy way to assess this. So just mathematically, when K minus 1 times A is much larger than K2, then the reaction is first order. So let's look at that limiting condition a little bit more. So what is the rate equation if I write it out? RB is equal to K2 times K1 times A or A squared. If I'm at this condition, is it A squared? No, right? That cancels out. Divided by K minus 1. So again, if I'm observing this behavior, do I know that there are 3 rate constants if I take rate data and I see a first order response? Right. I can't separate these. I can't determine them separate from one another. So we call that K effective, meaning that it has the form of a rate constant and it effectively acts as a rate constant, but this K, this lumped K, is not associated with any single elementary step. Now, K's in general and this should be review, I hope. Everybody seen that before? The Arrhenius equation? Okay, so generally speaking, I can write K in relation to an activation energy. What is that relationship for K effective? In terms of the activation energies of the elementary steps. Somebody, it's not the rate determining step.
It's the sum or difference of them depending on how they're arranged.
It's the sum of them, yeah, depending on how they're arranged. If you solve this out, what you're going to get is that K effective, this is going to be the product of the pre-exponential factors for 2, 1, and minus 1. We'll just call that A effective. But then, if I want to leave this up here, I can either write it as effective, but that's not very interesting, but I'll do that to start. But yeah, how do I relate E effective to EA? It's the activation energy for step 2 plus the activation energy for, double check, 1, yes, minus the activation energy for step minus 1. Does everybody see that? It's in the exponent, so when things multiply together, I can move it to summation term.
Is it negative because it's at the bottom?
Yeah, it's negative because, that's exactly right, because it's at the bottom of K effective. And just as a reminder, if I'm writing out this reaction coordinate diagram for step 1, this is EA1, right? What is this difference? Sorry. It's the activation barrier for the reverse reaction, EA minus 1, okay? And the sum of those two, or the difference, excuse me, this minus this, this minus this, EA minus 1 is equal to the reaction energy, which is this difference. So I can relate all of these back to simply the thermodynamics of the elementary steps. Can activation barriers be negative? By definition, can a transition state be more stable than the reactant or product state? No. So can an activation barrier be negative? No. Can an effective activation barrier be negative?
Yes.
Yes. Yes. All that means is that this is larger than the sum of those two. And I haven't told you anything about this reaction that would disqualify that assertion, right? That is absolutely positive, or true. Let's say that. All right, so effective activation barriers can be negative. Ones for elementary steps cannot be, okay? And again, this is very common within catalysis, so I'll just show you an example of what this can all mean. Let's say that I have CO in the gas phase, okay? And I adsorb it to some surface